Hi everyone, thank you for coming to my talk. So I'm Mario Polino. I recently got my PhD from Politecnico di Milano, working mostly on malware analysis. So I'm gonna talk to you about the anti-instrumentation and evasive malware, okay? So this is the agenda for my talk. The talk is about Arancino, a framework that we developed to contrast the evasive malware. So before actually explaining you how we did it, I'll give you a brief introduction on dynamic binary instrumentation, and then I explain you how to create some evasion or detection for this kind of analysis. Then I'm going to talk to you about an experiment we did, a measurement about how much evasive malware are actually using those kind of technique. And I'll briefly show you, talk to you about an unpacking tool that we implemented on top of our evasive anti-instrumentation system. And at the end, I'll give you a really quick demo on our tool so that you may want to use it. Okay? So let's talk about arancino or arancini. So this is actually an arancino, okay? So it's an Italian delicious food. It's a bowl of rice deep fried with inside meat and peas, okay? So you may wonder why we have arancino. So me and Andrea used to eat a lot of this arancino during the night, the banking stuff. So at some point we decided that we had to name something after arancino. And we named this tool after this one. So if you go to Italy, you should really try that. Yeah. Of course, I'm not going to talk on how to make this arancino. I may call my mother to have a talk on that, but I cannot make that. So this is the arancino I'm actually going to talk to you about. Okay? So it's a framework. He has many modules, and we can combine them to have some to defeat evasive malware. So I don't want to start explaining you the whole framework and then show you the how we use it. What I'm gonna do is I'm gonna show you each technique or most of the evasive technique that we found, and I'm gonna explain you the right module that we used to defeat that technique. Okay, that's the plan. I show you the evasive technique, and then I show the module that can contrast that technique. So before actually starting doing this journey about the anti-instrumentation, a brief introduction on malware analysis. That is what I do. So malware analysis is the way that we use to actually understand what a software is doing. You know? We may discover if something is malicious or not looking at its behavior. And historically, we have two kind of big technique, the static malware analysis and dynamic malware analysis. So the static analysis is usually the stuff about reversing the code, building the control flow graph, and so forth, so on. Okay? And that's not the part I'm going to talk about. So the static analysis has a big limitation, that is, I can obfuscate the code and then it's harder to deobfuscate and look at this stuff. So people came out with what we call dynamic malware analysis, that is actually looking at the interaction between the software and the underlying operating system. So I can trace down system call, files, I can look at the memory, all this kind of stuff. And this makes it much easier to actually perform this kind of analysis. So the problem with the dynamic analysis, to have this control on what is happening, usually people do what is called instrumentation of something. I can instrument a virtual machine, I can instrument an emulator, or I can instrument a binary. But because there is this kind of instrumentation, we can write code like that, okay? I can check if for small differences between what I expect from a bare metal execution and from an execution that is actually made inside an instrumented environment. So if I found those little differences, then I can write this kind of code. If I'm under analysis, I I don't do anything, okay? Otherwise, I can be malicious. And this, of course, defeats the purpose of dynamic analysis, okay? So those small differences are what we're gonna call artifact, okay? There are some artifacts introduced on the system because you did some instrumentation. You are not using bare metal machines. Okay, cool. So let's talk about dynamic binary instrumentation. So the dynamic binary instrumentation is one kind of instrumentation that you may perform in order to perform malware analysis. And the idea behind dynamic binary instrumentation is that you don't need a virtual machine or an emulator, okay? What you do is actually adding some code inside the executable. So you have the executable, you add something inside that is actually logging and perform the analysis that you want, using the tools that are called DBI. So to understand how a DBI works, we actually need a bit of introduction on how the binary is made. You know? So you have basic blocks that are basic instructions that are executed always together, and they are connected by jumps, and they build the control flow graph. And then if you take a set of basic blocks that are connected together, you get what is called a trace. Okay, a trace is a multiple basic blocks that usually are close enough to be executed almost together. And most DBI tools actually instrument a trace at a time. So they load a trace, instrument the trace, and then they load another trace, and instrument the other one. So how they do that? They took a trace, they copy it in some other part of the memory that is called the code cache. And then they use what is called a JIT compiler, just-in-time compiler. Okay? So it's something that as an input the original code and something that you want to add, okay? And it's actually recompiling your binary code, adding this stuff inside, okay? And you can, the great thing about dynamic binary instrumentation is that you have a really fine-grained control on what you are doing, okay? You can insert instruction between certain specific instruction, between basic block, between trace. You can search for read instruction, for syscall instruction, for interrupt. You have a really fine-grained control. And this is the great advantage of using DBI instead of using a virtual machine or an emulator. Okay. So, so those are the 4 DBI tools that I know. Okay. Some of them, like Valgrind and Revenge, they actually works only on Linux, as far as I know. And the one we actually use is intern pin, that is actually the most used, and it's also the one that is actually better documented, usually. So all the talk is based on pin, okay? So let's talk about evasive malware then. So, and the artifact. We actually divided all the artifacts that we found by what they are checking. Okay, so we come up with basically 4 categories that are those ones. So we have cold cache artifact, git compile detection, environment artifact, and override detection. And I'm gonna go through all of them. So let's start with cold cache artifact. Okay. So what are the cold cache artifacts? They basically are all the artifacts that exist because you are using the code cache. Okay? The code cache is the one I just explained you, is the part of memory that the dynamic binary instrumentation tool is using to create the instrumented binary. And we can basically have 2 kinds of code cache detection. The first one is instruction pointer detection, okay? The fact that you are actually executing something inside the code cache and not something inside the original text section, it means that your instruction point is different and you may detect this. So how you can detect this? We basically have 2 ways that are actually working. The first one is is the one of using the interrupt to E, okay? That is the instruction that was historically used for doing the anti-sys code. Okay, when you call the interrupt to E, you have as a side effect that the current instruction pointer is copied in the EDX register. And this is one time. The other one is using some instructions that are actually related to floating point context. If you use one of those instructions, they are basically storing on top of the stack information about the context that actually contains also the instruction pointer. Okay? So if you call into E, you get the ADX with the instruction pointer. If you call fsafe on this instruction here, you have the instruction pointer saved on the stack. Some of you may wonder, I can do other tricks like I can call 5 instruction ahead, so so that I have on the stack the instruction pointer. If you know how the call works, is pushing on the stack the instruction pointer. But using the call is actually already handled by pin, and so pin is already because of how pin works. You basically will not end up with the code cache instruction inside the stack, but with the original one. Okay. So the only two I'm aware of are those two ways to actually identify the instruction pointer. So we did this before, but we have a module that is called the pattern matching module, okay, that we're gonna use to defeat this technique of instrumentation detection. So the pattern matching module has basically 2 components. The first one is what we call the patch map. It's basically a list of instructions that we know can be used for detection, and then function pointer that are basically functions that gonna patch the result of the of our instruction. And the patch dispatcher is basically the module that is actually during the build of the trace is actually going to search for the instruction, okay, to patch. Okay, so I'll give you an example. Here on your right, actually, so you have the trace, the original trace, okay? In the middle we have the patch dispatcher, and on the left is the patched trace. And the idea of the patch dispatcher is that you are loading each time one instruction, you are checking inside your list if it's a blacklisted instruction. If it's not, you're gonna save it as it is. If you have one of those instructions, what you do, you just add, okay, the patch function for the specific instruction. So, how the patch is working. So here I'll show you we know that into E is basically storing inside the register EDX the wrong instruction pointer. So the patch is easy as you may think. I just change, okay, the value inside the register, okay, and that's all you need to actually patch this. For the floating point, instruction, you need to patch the memory inside the stack, but the principle is basically the same. Okay? Cool. So that's the first example I showed. And then we have another one that is even more interesting. That is the self-modifying code. So the idea of self-modifying code is the code that is changing itself during the execution. So I'll give you this example. I have a set of instructions that you can see here. And one of them, the third one, is what I wrote as wrong instruction, okay? It may actually be literally something that cannot be disassembled, so it's wrong instruction, or it may be something like some privileged instruction, like in-out, something that you need to be in at ring 0 to execute, okay? No, you cannot execute in user mode. Or it can be some access on memory that you know it's not allocated. So the idea is something that is crashing the program. So what happened with self-modifying code is you have code like this, you collect the trace and put it inside the code cache. And then you start executing. And the first instruction is actually changing the third one to an instruction that can be executed. Okay? So you keep executing, and when you reach the instruction 3, the patch happens only on the original text, so you execute in the code cache and you get a crash. Okay? You die. You identify that there is something wrong. So we want to fit that. So we write a specific module for self-modifying code. And it has basically two functions. One that is called mark-written address that we put before each instruction that actually writes something inside the memory. Okay? And the other one that is check IP written is basically put before each instruction. So what we have is something like that. So instruction 1 is actually writing something in the memory, so we have both the function. The other are not writing anything, so we have only the check. And then it's easy. When we execute, before actually executing the first instruction, we check which part of memory is gonna write, and we store it in a list. Okay? Then the patch happens, and every time that before actually executing each instruction, we're gonna check the list to see if the instruction we are about to execute is an instruction that has been modified or not. Okay? So the instruction 2 has not been modified, so we can go on. When we reach the instruction 3, we know the instruction 3 has been modified, so we just trigger an invalidation of the cache. Okay? We actually trigger what is called a trace recollection. So basically the cache is invalidated, so we recollect the trace from that point on, and now the new trace actually contains the instruction patched. So we can keep executing because we have the new instruction. Okay? So that's the idea. It's kind of heavy, as you may think, because we are basically adding something on each instruction, but it's working. Okay. So that's for the first part. So now I want to talk about environment artifacts. So you may see environment artifacts as the, let's say, miscellanea of the artifacts, okay? Are actually those artifacts that are not specific about the JIT compiler or the code cache or the overhead detection, okay? We have some that is trivial and some that is less trivial. So the first one, the trivial one, is parent detection. So we can basically check the list of process and say, oh, okay, my father process is spin, so I'm anti-instrumentation. Okay, it's easy as it is. And there is two ways you can check your father. There is one using Windows system call, so the querying system information, and the other one is looking inside the CSRSS process. That is actually a userland process that keeps an entire list of processes inside its memory. So you can read it from its memory. So we can easily defeat this with hooking modules. Okay, hooking is something that is well known. So in the communities, the idea is I intercept some function, I hooking some function. We implemented in our framework two hooking modules. One that is the function module, and the other one that is hooking the syscall. So the second one is working, searching for the instruction, for the syscall instruction, the one that is actually triggering the syscall, adding something after. And the first one is actually different because it's on the LLL. So the idea about the module is that when you are loading a new DLL inside the memory, you check with a dispatcher if some of the function inside this DLL is on your list. So if it's on your list, what you do is actually putting a jump at the beginning of the function. It's the classical hook. You put a jump at the beginning of the function, and the jump is jumping inside your function, defined in another place, doing whatever you want, and jumping back. Okay? That's a pretty standard way of hooking functions. And what we can do is basically hooking the anti-query system information and changing the value returned by the function. So if there is pin, it's a blacklist. If there is pin.x inside, I change it with common.exe. Okay? Just a blacklist. And to deny access to the memory of other process, we hook the anti-open process. Okay? So that basically when you try to opening the memory of the process, you basically cannot. Of course, done in this way, you may think, oh, but if I cannot have access to this process, it's a way to detect the system. And this is true, but you may use other module to actually, I'll show you later, to actually fake the read of memory. Okay? But if you implement in this way, then yes, there's another artifact basically introduced by this. Cool. So, and this is the parent detection that is pretty easy. So, the second environment artifact that I want to show you is what we call memory fingerprinting. So, the idea of memory fingerprinting is you can start looking inside the memory for strings, for binary sequence, for whatever is actually something that you know it's from pin. You know there is the pin tool DLL inside the memory, so if I start searching in the memory, at some point I'm gonna find the pin tools. If I find it, okay, I know I'm under instrumentation. So the problem of searching the memory, like I show you going back and forth, is that you cannot jumping around with any address inside the memory, because if you end up in a place like this, that is basically some memory that is not allocated, you basically get a crash. You know? So you cannot go through the memory like, okay, start from 0 and then I try every address. And so to search through the memory, you usually use some call, so some system call, asking the operating system about the memory layout. No? The idea is, oh, I use the virtual query and then I ask to the operating system, these memories are allocated or not? And then the operating system is telling you, yeah, it's allocated or not. In this way, you know which is the memory layout, and you just search inside that, that memory that you know is allocated. So you may guess the way we used to trick this. We basically hooked the virtual query, and we created a whitelist of accessible memory. So that every time you try to query the system, it tells you that the free memory is only the one that you want to show. And the memory list is actually updated at runtime, okay? So inside the list, we have the main module, of course, the text module, and then the library, and there is another hook inside the load library, such that if you're actually loading a new library, we know it, if you're loading later, so we can add to the whitelist. And of course, you have the heap, the stack, and then you have some of the Windows table, and the mapped file. Okay, when you are mapping something in the memory. Okay, so that's the second step. We are halfway there. Okay, so stay with me another 20 minutes. So Git compiler detection. Okay, we are using Git compilers, and actually it's not Git, it's Git compiler. So I can detect that I'm using this stuff compiling inside the memory, no? So one of the way to detect a Git compiler is usually looking at the permission of the pages. because you are writing the code that you want to execute, your pages will have writing and executable permission. So you can just list the pages and see, oh, okay, I have a lot of writing and executable. So I didn't use any on my malware, so I know this, there is something odd. And so, and this is the problem with the memory pages. And another thing that you can do is you can detect that someone hooked some functions, okay? And pin is actually hooking some function to perform its tracing of rebuilding and so forth, and all this stuff. So I can look inside the memory of a DLL, inside some functions that I know pin is gonna hook, and if the beginning of the function is not what I expect, I know there is a hook. So that's actually the example. This is the example on how pin is hooking the user APC dispatcher, okay? So it's basically adding a jump at the beginning, as I show you. So I can read it, and I know I'm an instrumentation. So we have a module for that, of course. So it's called the fake read ender module. What it does is basically, you can see as a virtual memory on top of virtual memory, okay? I'm gonna show you now. The idea is I have the function there inside the memory, and what I'm expecting there is this LIA instruction. But of course, it's hooked, so I have a jump instruction. So when we are building the chase, we search for instructions that are performing a read inside the memory, like the move here, okay? So it's reading inside the memory. We keep a list of hooked functions inside another part of memory, as if the memory we are going to read is inside our list, we basically redirect the memory to another address where we stored the real value. Okay, so every time we actually perform a hook, we save the old value somewhere else, and then we keep a list of where are our stuff, where we put the old value. And when you are trying to read the beginning of our function, we just change the address on the instruction so that you're gonna read another place. Okay, so you read the original instruction, and then you are fine because all the compare and check that you are doing is actually what you expected. So we have another thing that is memory allocations. So the JIT compiler inside pin is actually performing a lot of memory allocation. So every time you need more space for building its trace, it's actually allocating something. So another easy way to detect the JIT compiler is the one of hooking the virtual memory function. Okay, so I'm the malware. I'm making the hook on the allocate virtual memory, so I can actually count how many allocations are there. Now this is how it works. There is our function there. I put the jump back. I increment a counter, and then I jump back. In this way, I can count how many allocations are there. And you may not perform any counting. So if if the counter is greater than 0, you know that basically you're under instrumentation. So what we did is actually, so this is how it's happening in the hook. Okay, you are the malware. At some point, you are writing inside the jump. So what we did is actually, it's similar to the read stuff I just showed you, but this time with the write. So we basically using the fake write ender module that is basically stopping the write, or what it's actually doing is redirecting the write somewhere else. Okay, so we basically change we list while you are building the trace, we are checking for all the instructions that are performing a memory write, and then we change the address, putting the write something in another place we allocated for some reason. Okay. So of course, what we do is when you try to read that memory allocation, we still have the module that takes the reads, so we can basically redirect the read also in the same place you wrote. So as a malware, you are thinking to write inside the NTDLL or reading there, but basically everything you are doing on that address is redirect somewhere else. Okay? So you perform the hook, you think it's fine because you're reading back the value you wrote, but actually there is no hook in place, and so you cannot count any allocation. Okay. So we are almost there with the instrumentation, anti-instrumentation part. This is going to be a bit quicker. It's about overhead detection. So this is also a kind of well-known technique when you are performing any instrumentation of any kind, actually. So I count the time. I count the time my script, my executable is taking to perform some action, and because there is some instrumentation involved, I'm actually my execution is going to be longer than expected on a bare metal machine. Okay, so this is of course also true with ping. It's even more true if you use module like self-modifying code that I show you, that it's adding an instruction every between each instruction. No? So there are two big ways to actually detect the overhead. The first one is you basically check the time using the Windows functions. So there are two API that are called getTickCount and timeGetTime. That are basically giving you the execution time. But what those API are actually doing is reading from a memory structure, a structure inside the memory that is called k-user shared data, that basically have some value, some counter that is keeping there. So you may guess the solution here is we use the UKIM module for the getTickTime, and we use the fake read module for user shared data. This part is not automatic as you may think, because the problem is which value you're going to put inside there. Okay, and how is it right now is kind of manually. So we estimated the value for our tools for our framework. Okay. And we are using a fixed value there, but you can change it if you are using with the other value that you may think it works. And there is another way to actually detect the overhead of your program. That is using the RDTSC instruction. That is actually the instruction is giving you the count on CPU cycle. And also here you right now may already know which part of the tool we want to use for that. We use the pattern matching module. That is the module that we also use for the int2e. No? It's the module that is searching for some instruction and then patching, adding some function after the instruction. So you just change the return value of this instruction here. Okay? So that's enough for the anti-instrumentation. Now I'm going to talk about the experiment we did on evasive malware. So our idea is we had this tool, okay, and then we know, okay, it's useful, it's not. We don't really know because we don't know how many evasive malware are out there. So what we thought, okay, let's have a bunch of malware and try to understand if they are performing some evasive behavior or not. So that's basically what we did. We collected about 7,000 binary from virus total, with the condition that they are detected at least from some antivirus, because we want them to be malicious. That's the idea. From October to February last year, okay? And we run it actually on a virtual machine. That's because we need to run 7,000 binary, and we don't have 7,000 bare metal machine. So the experiment has been done inside the virtual machine, but we were checking for anti-instrumentation techniques, so for dynamic binary instrumentation. Of course, we may have some false positive because the malware was actually detecting the virtual machine and not the DBI. But anyway, we tried our best to make the virtual machine as complete as possible. So we installed a bunch of application. We even stored some credentials, some cookies, some browser history. So to be as real as possible. And of course, we had the moving mouse and some other tool that were launching application, this stuff. And we ran each application for at least 5 minutes, okay? So those are the results, more or less. So from all the binary we collected, we ran them through AV class. That is this tool that basically give you the family of the malware. So the name that you see here is the name given to you by the AV class. So what you can see here is that we have a really huge number of verilog. It's like 80%. So this is how much of this specific family were inside our sample. So there are many verilog, about 9%. We think that it's because during February and actually during October and February, that was more submitted than others. I actually talked with the guy who developed vClass, and he told me that verilog is not so common as a family inside their tool. So this is the reason. And what you see in the middle is the percentage of sample of that family that is evasive. So like verilog is almost always evasive, but for other, you see that they never triggered any of our technique. And of course, on the last column there, you see how many different techniques they triggered. Okay, so this table may be more interesting. Here we basically ordered the family about the evasiveness. I mean, the first one is the one that is 100%, and so on. So as you may see, there are a few families that are basically 100% evasive. They always implement some sort of DBI anti-instrumentation technique. And there are some other that actually have few samples that implements those techniques. So let's see which technique they actually implement. So the first one is the self-modifying code. And this is not actually surprising, because self-modifying code is not only used to defeat dynamic binary instrumentation. It's used for many reasons. It can also be like a side effect that is actually breaking also DBI, if you want to be honest on that. But the second spot is kind of more interesting, because they are doing the parent detection check, many of them. That is a super easy trick, so that's probably the reason, because many malwares have it implemented, but it's also one of the easier to actually bypass. You know? And then we have other, so the write on protecting memory region, it means basically it tries to hook something, okay? And we have other classic stuff like the debug flag, or and very few they actually did memory fingerprinting, so searching through the memory for stuff. So another disclaimer here: the memory fingerprinting may not be done to actually identify PIN. It may be done to identify other stuff, but they were doing memory fingerprinting somehow. Okay. So about overhead of our tool, because as I told you, all this stuff doesn't come for free. And here I just show you some rough number on overhead, and the percentage overhead is actually on top of pin overhead. Pin has its own overhead, so when you say we need to use the fake read module, 254% it means on top of pin instrumentation. Okay, and we don't have one for the self-modifying code because the self-modifying code was not working without our implementation. It basically was crashing every time. Okay, we are almost done. This is a feature that we have in our tool. So last year at Black Hat USA, the few guys who actually developed part of this stuff, they have a talk about unpacking, an unpacking tool that was called Pindemonium. So Pindemonium is actually integrated with arancino, okay? And Pindemonium was doing really neat stuff like detecting the bright and executable region, was dumping the program, identifying the original entry pointing, and at the end was also able to reconstruct the executable sometime. And so you have all this stuff on top of I can enable some anti-evasive system. So last year we weren't supporting at all Obsidian that is actually doing some anti-debunking test, anti-debunk check. So now our tool can also handle Obsidian as an unpacker. So for the one of you didn't follow the talk, the green spot means basically we can fully recover the executable. It means that the output is an executable that you can run. The yellow means you have the unpacked code, but it's not runnable because we failed to detect the import table and this kind of stuff. Okay? And the tool is actually working on many. This is an experiment we did where basically trying to unpacking random stuff, and it works on more than 60% of random packers. Okay, so they've been randomly chosen from VirusTotal. Good. So demo time. So I'm gonna show you quickly how to use the tool. So for the demonstration, I'm actually using X8. X8 is a tool written by some guy from Core Security. And they basically they have implemented some of those techniques I just showed you. So I have a VM here, and I tried 20 times this morning the demo. I hope it's still gonna work. So we have the X8 binary here. Okay, and for example, I can tell, okay, detect by into E. Okay, it's a DLL actually detecting if it's using the into E instruction to detect the instrumentation. Of course, I'm not using pin, so detection failed. So if I actually use pin, you see that it's detecting pin. So let's use our tool. And we have many flags that you can enable. So anti-ev is the generic flag. For the instruction specific patch, you need to use the anti-ev instruction patch. And now you see it's actually not detected anymore. Okay. So I have another couple of stuff I can show you. We have the parent detection. So parent. Okay. Parent. Okay. And you can just use the anti-ev flag to defeat that. There's two, okay. Okay, or another one that is cool is the one that is actually hooking stuff. So it's detect anti-ELL hooks. Okay, and you can use the anti-read if I recall correctly. Let's read. Okay, this stuff. So I can spend all day show you the stuff, but that's almost it. So okay, so let's wrap up the talk. So I show you that some anti-instrumentation technique. I show you a framework that we built to defeat those techniques selectively. You can enable some part or other, and you can eventually use the framework to implement some other patch that you want to add for other reason. And I show you that there are actually malware that are using those kind of technique directly to defeat pin or not. And I show that we have a packer that is actually evasion resilient right now. So that's almost it for my talk. And you can find the tool on GitHub. If you're going to go there, you can download it. We also, I think, have some samples to check the stuff. And right now, if you have any question, we can chat about this stuff, or if you want to. So there is someone with the microphone, and you can ask a question on the microphone, or maybe we can talk later. I'll still be around for a while. Definitely want to follow the following talk. So, okay, let's go. I have some questions.
Okay, guys. What are the questions that you would like to ask Mario?
Okay. There is a question there.
Here it is.
Quick question on the way you were detecting JIT emulation. You said that at every step you were basically checking what's the address, if the address is the one of the binary.
Yeah.
So, yeah. So why didn't you just map those pages as read-only and then trap on executing a write those pages? So the pages where you map the original text file.
So you're saying, let me go back. You're saying why we. So the question was about the fake read module, right? So why we redirect the read instead of catching the read and stopping it?
Yeah, so you basically have, in one of your prevention techniques, you basically have after every, read, you have, where do I check the PC? Check the PC against the table.
Oh, was the self-modifying coding maybe?
Yeah. Yeah.
Okay, so your question is
Why don't you just map the original DLL pages as read-only?
Because the self-modifying code was about the malware changing itself. Okay, yeah. So
So you need a write.
Yes, it needs to be to change it itself to actually works because it's not fully functional. Okay, so it's changing itself in a working version. So at the beginning, it's not working because it has the wrong instruction. So it is patching itself. So we don't even know how it's gonna patch it before the execution. So we cannot like redirect the read or this kind of stuff. So we came up with this solution. I think it can be improved. I mean, of course, checking for every instruction, we may do something like re-instrument only on those memory addresses that are marked inside our list, or something like that. I think this can be improved a bit, but yeah, the reason because we are not mapping, we are not catching we are not mapping read-only or whatever is because we are not controlling we don't know what is gonna write. Okay, other question.
Have you ever used the tool to diffuse packing like... oh yeah, no problem. I think I have enough voice, but okay. So have you ever tried to use the tool to diffuse protection and packing mechanism like mProtect or VMProtect or, for example, Demida, stuff like that, that are obviously the most complicated to...
Yes, so I think the problem with Demida was that our unpacking tool is not able to unpack Demida.
Yeah, I am a reverser. I know quite well that it's very difficult to achieve that. So I'm really interested in understanding the approach that you use. Well,
so the unpacker is not handling Demida, and we didn't try to run it with the anti-evasion stuff, but I actually may try to do now that you said. So to answer your question I have no idea if it's going to work.
No problem. The other thing is about the set of samples that you have collected from VirusTotal. Mm-hmm. I normally am facing malware that is very low in terms of ratio from VirusTotal, about 1 or 2, just because the antivirus is definitely not enough to be able to catch that stuff. So what I'm asking is, have you ever tried to analyze with this tool malware that even available from VirusTotal have low ratio, but definitely is malicious because it's reported by, I don't know, APT groups and study upon APT groups?
So some of the stuff we analyzed actually had low ratio. So our limit was at least 3 antiviruses, so that we know it's malicious. So I don't have numbers on that. I didn't check which one it was low rate, if I had more evasion. But this is actually another interesting number to actually have and show. So we had for sure run it on low ratio malware, but I don't have the numbers.
Okay, thank you very much.
Next question.
Do you think you can extend this to other dynamic binary instrumentation tools, like create a library or something that can be added?
Sorry, go ahead.
Yeah, please read.
Okay, so more than other dynamic binary instrumentation tool, what I was thinking about is to extend to other detection mechanism like VM detection. So I may use PIN. Okay, right now I'm using PIN to avoid PIN detection because PIN is powerful enough. But I may use also PIN to avoid VM detection or to avoid another emulator detection.
Yeah, I'm okay with that. But there are companies and people that use different custom dynamic binary instrumentation
I see.
tools. And I see this as a useful thing, like a library that can be easily added in their systems. So the problem with that is that I don't have access to those tools. So it's kind of, as I show you, many of those techniques are kind of on point of kind of specific on PIN. Okay. So you need to know how the tool is working to create those instrumentation. But I mean, the framework is already there to be used in this way. Okay, so it's open source?
Yeah, it's on
cool.
GitHub. Yeah.
Okay.
So let me show you. You can search arancino on Google, but add also GitHub, because if you just search arancino, you get the Italian food. Okay? So if you go on GitHub and search for arancino, you'll find it. I have the link at the end.
Sorry, I have another question. Okay. What if your tool, your dynamic binary instrumentation tool, uses those functions that you actually patch, like anti-virtual whatever, that read the memory and...
So you're asking if the
DLL, the anti-DLL functions.
If the malware try to hook that stuff?
No. If your dynamic binary instrumentation tool actually uses those.
So he is using some of them,
so we don't change the hook of the binary, we just hide it with the fake memory read.
Okay.
Okay. So if there are no other questions, I thank you all for coming to my talk, and see you.